This video introduces Bifractality of Fractal Scale-Free Networks by Jun Yamamoto and Kousuke Yakubo. The paper focuses on the intricate structure of large-scale networks, specifically fractal scale-free networks. To understand the properties of large-scale networks within homogeneous structures, a common simplification is to ignore degree correlations. However, for networks where degree correlations are significant, focusing on the fractal nature of the network is beneficial for investigation. Multifractality generally refers to a certain type of scaling law applicable to systems that have some measure. In the context of networks, it specifically indicates a scaling law that relates to the network structure. If a network is not only fractal, but also scale-free, the network may possess a bifractal structure, in which two local fractal dimensions suffice to characterize its fractal nature. Previous research has shown that networks can possess bifractal structures under certain conditions. However, it remains unclear how commonly these conditions for bifractal structures are found across diverse networks. Based on their research, the authors propose a core conjecture that any fractal scale-free network may inherently be bifractal. To investigate the conjecture, the authors analyzed 4 types of fractal scale-free networks. They initially demonstrated that deterministic hierarchical fractal scale-free networks, created using the single-generator model, inherently have a bifractal structure. This finding was verified for various deterministic hierarchical fractal scale-free networks by comparing theoretically predicted mass exponents with those obtained through numerical calculations. The authors then explored stochastic hierarchical fractal scale-free networks, which are hierarchical but not deterministic, using a multi-generator model. Their analysis indicated that networks formed by this model also exhibit bifractal structures. They also demonstrated the presence of bifractality in non-hierarchical fractal scale-free networks. This was done by analyzing the giant component of a scale-free random network at its percolation critical point. Finally, they showed that the mass exponents of 2 real-world fractal scale-free networks match the anticipated bifractal profiles based on their degree exponents and global fractal dimensions. Based on these findings, the authors conjectured that any fractal scale-free network may inherently be bifractal. The authors further investigated local fractal dimensions. In a fractal scale-free network, 2 dominant local fractal dimensions have distinct implications. In the thermodynamic limit, the lower local fractal dimension describes substructures around infinitely high-degree hub nodes and finite-degree nodes at finite distances from those hub nodes. In contrast, the upper local fractal dimension characterizes local fractality around finite-degree nodes, infinitely far from the infinite-degree hub nodes. In a finite network, as illustrated in the figure, the network exhibits local fractal dimensions that are not extreme values, but rather fall into an intermediate range. Their study on the bifractal nature of fractal scale-free networks enhances the overall understanding of dynamics such as synchronization and information spreading in these networks. The authors advocate for future research to unravel the relationship between spectral dimensions and the bifractal structure. Such studies are crucial for developing a systematic understanding of dynamics on bifractal networks, paving the way for more advanced network analysis and modeling techniques.